So the next observation is to look at the characterization of the orbit in terms of this subset, that is the set of all eventual images of a particular point of omega. So if you consider an orbit of omega, of alpha in Tn, and a point P of the orbit, then the point P will belong to the kernel of the orbit if and only if the set of all eventual images of P coincide with the entirety of the orbit. So we look at the proof of this. So let's suppose first that P is in the kernel of the orbit. If this is so, then by the lemma, the previous lemma, the lemma we proved last, the kernel of the orbit can be written as P alpha square up to P alpha r minus 1. Because the lemma said any point you pick from the orbit and apply alpha r times, you come back to the point, and the set of distinct elements P alpha square will constitute precisely of the members of the orbit. So with this last property here. So it then follows that the kernel, because each one here, if you keep on applying alpha on every point here, you still come back to P. Even when you apply alpha r times on P, you still come back to P by this very equality here. So therefore it means the entirety of this set is inside our set of eventual images of P. So therefore the kernel of the orbit is contained inside the set of eventual images of the point P. In the converse, well, because we are trying to establish equality, so the way we do here is to see that since we assume this point is in the kernel, and then we want to show equality, so if the kernel is contained in the set of all eventual points, so how about elements of the orbit that are not inside the kernel? So for example, if we take a y outside of the kernel but inside the orbit, then by lemma 3, y will eventually arrive into the kernel. So there is some t such that y alpha t is in the kernel. And so once you are in the kernel, you will arrive at P eventually. So if we keep on applying alpha on this y alpha t, we will arrive at P. So therefore it is clear that equality will hold, because it is then clear that we can find some u less than or equal to r, such that if we still continue to apply alpha on this particular point here, y alpha t, if we apply alpha on it r minus u times, we still hit this point P. And so therefore it means starting with y, we can still arrive at P. So therefore it means y is a point of this set of eventual images for the point P. So that means the entirety of the omega is also contained inside the subset. But this is a subset of the orbit omega. And so therefore equality holds, because omega is contained in the subset, and the subset is clearly inside the omega, and so therefore we have the equality. In the converse, if we assume equality for that the set of eventual images for this particular point is equal to the omega, the entirety of the orbit, then this is clearly pronouncing that P is inside, because P is a member of the orbit. So therefore P is in the set of eventual images. And then by the equation 1 here, up here, the equation 1 is saying P is in the set of eventual images if and only if P is in the kernel. So therefore P will belong to the kernel. So this is actually, this is our last observation for the properties of the kernel. But before we round up this discussion, let us look at an example. If you look at, if you consider a map alpha in T14. So we assume n is 14, and then we pick this particular mapping alpha, where 1 and 2 are mapped to 3, 3 and 6 mapped to 4, and 4 is mapped to 5, and then we have, and so on. So therefore 14 is fixed here. And then from the last discussion, we talked about the directed graph associated with a particular mapping, where we'll have an arrow from 1 to 3 because 1 is mapped to 3, and then 2 to 3 there will be an arrow, and so on. We develop a directed graph like this because 1 is mapped to 3, and 2 is mapped to 3, and 3 is mapped to 4, 4 is mapped to 5, and so on. So we develop a graph like this. And so this is because these two orbits, this last two orbit here, these are orbits that are entirely contained in the image set, because every element of the orbit is a member of the image. So omega 3 and omega 4 are contained entirely in the image, and so these are the orbits that form a cycle. So since this is a cycle of length greater than 1, we call it an acyclic orbit. And this is a trivial orbit as we defined in our lecture 4. But then these orbits are not entirely contained. The two orbits here are not entirely contained in the image set. There are points not in the image, like 1 here and 2 and 7 and 8. They are not in the image. So but then this orbit has some kernel. We can see the kernel of the orbit, and this is the kernel of the orbit. And the size of the kernel here is more than 1. So this is a standard orbit. This is a acyclic orbit. So you can see the kernel of this orbit and the kernel of the other orbit. So these are the kernel. Kernel is always the cyclic portion of the directed component of the graph associated with that particular map. And so this is what we see. And you can see that if you pick any point from a particular orbit and keep on applying alpha, for example, if I start from 2 here and apply alpha a certain number of time, I will eventually hit a point of the kernel. So if you apply alpha once and alpha 2, so 2 alpha square will get you to 4, which is already here. And likewise, if you take any member of the kernel, because this is a kernel of size 3, and apply, if you take 5 over here and apply alpha 3 times, you come back to 5, and this is what we say. So like for example here, you can see that this is already a kernel of length 1. So if you take 10 and apply alpha, you still come back to 1 because this is a fixed point. So these are some of the observations we have looked at in this particular lecture. Thank you very much for being with me, and I hope to see you in the next discussion, where we will look more into the properties of finite full transformation.